As systems manage higher volumes of complex data, developers increasingly turn to index data structures to enhance performance in locating a given data object. Used properly, indexes can boost speed logarithmically beyond that of a linear data search. However, when indexing is contemplated, the first and often the only index to be considered is likely to be the B tree, as Chris just mentioned. Out of all the indexes that can order records in database management systems, only B trees are offered universally. And often they're the only index offered, and there's no denying B trees' efficiency for basic database search operations like exact match, prefix, and range searches. But these plain vanilla indexes are often a poor fit for certain data and access patterns, such as IP routing, geospatial searching, and in-memory database systems. Therefore, it pays for a programmer to understand a wider variety of indexes that may at first glance appear more exotic. Diverse index types enable important design trade-offs involving search performance, memory consumption, and update performance, and some indexes offer distinct advantages for certain application categories. This presentation is going to examine less well-known indexes that can be a good fit for certain application needs. The B tree is the most popular data structure used in database and file systems and provides efficient, general-purpose lookup and sorted retrieval of entries for a large volume of data. We'll look at R trees for geospatial indexing, which is common in GPS and navigation type systems. We'll examine the Patricia Trie for router and telephone directory searches. This is also known as a longest prefix match index. T trees are appropriate for all in-memory data storage and access. Whereas the design goal of a B tree is to minimize I/O, the design goal of a T tree is to minimize memory use. Hash tables can quickly locate a single unique index entry. Hash indexes can be faster and use less memory than either of the types of tree indexes. And then custom indexes are B trees that allow the application to define the collating sequence or the sort order of the entries rather than defaulting to a simple lexicographical or numerical sorting. And we'll look at a couple of examples of where being able to control that comparison function could be useful. All right, moving on to the Patricia tree now. So a B tree can locate values with a specified prefix. For example, finding all stock ticker symbols that start with the letter A, but some applications require a different search, locating keys that represent the longest prefixes of a specified value. Here, a B tree could also be used by performing several iterations, searching for different prefixes of the specified value starting from the longest, but that's inefficient. A much better index for prefix searches is the Patricia tree, which is a variation of the binary tree. The term tree, spelled T-R-I-E, is derived from the word retrieval, and then Patricia stands for practical algorithm to retrieve information coded as alphanumeric. The Patricia tree can perform tasks like phone routing, predictive text, and IP filtering. In the first case, given an incoming phone call and a table of operators with known prefixes, the right operator needs to be selected to handle the call. Predictive text is the functionality your mobile phone exhibits when it tries to guess the word that you're entering into an SMS text message. The last, and actually the most common case, deals with IP addresses. Given IP masks for valid or rejected domains, then a received HTTP request could be classified as accepted, rejected, redirected, and so on. And here's how to visualize a Patricia tree. The elements in a tree, which is a string in this case, can be retrieved by following the tree from the root to a leaf that ends the key. This particular tree that we're looking at contains the strings bear, bell, bid, and so on. One potential problem with trees is when the set of keys is sparse, the tree will have what's called high space complexity. In other words, internal nodes only have one descendant. The Patricia tree is a variation of a binary tree, except that it has a bit index associated with it and kept in every node. The index indicates where the bit comparison is performed. When a search is performed and the algorithm encounters a node, the algorithm compares the node-based index to the bit index of the search key and then branches left on a 0 and right on a 1. The bit index of nodes in the tree must decrease as distance from the root increases. That makes sense when you consider that we number the bits in a byte or a word or a double word, etc., from left to right, and we think of them as the high bit and the low bit. Thus, a parent node in the tree will always have a higher bit index than its children. A search on a Patricia tree is concluded when the algorithm follows an upward link. Wherever the algorithm ends after following that link is the result of the search. So again, a Patricia is a normal binary tree. The edges of the tree are marked with a sequence of bits that is common for all the keys included in the subtree and is in fact kept in the node itself. Moving along the tree is simple. Given a key, compare its prefix with a sequence of bits kept in the vertex or in the node. If they're equal, then bite off the prefix and check the next bit. If it's 0, go to the left. If it's 1, go to the right. If there are no more bits, then the key is found. If the prefix does not match the sequence of bits kept in the vertex, then we found the best match as opposed to the complete match. If we need to insert and the prefix did not match, then the vertex is going to be split into two, creating a new vertex as a root, and the common prefix for the two children is written into it. Patricia trees usually provide two search operations. Locating an object that exactly matches the specified search pattern, in other words, objects whose key values contain a specified pattern as a prefix, and locating the nearest match to the specified pattern, in other words, the object for which the key value and the specified pattern have the longest common prefix.